Factor it. So let's go ahead and factor this. It factors to x minus 4 times x plus 3, okay, and that's greater than 0. And then here's where the sign analysis comes in. We're going to set each factor, each group equal to 0. Now when we do that, we're going to get negative 3 and positive 4. Okay, so we're going to plot those on the number line, negative 3 and positive 4. Now we want this to be greater than 0, not equal to 0. So it's not going to include negative 3, and it's not going to include 4. If we put negative 3 in, that's going to be negative 3 plus 3 is 0. 0 times anything is 0, but we want it to be greater than 0, not equal to 0. So again, that's why these are open. So then what you want to do is you want to pick a point in each one of these three intervals. Okay, so I'm going to pick a point that's less.
You plug in something that's not even in the domain, like a negative root. What's the limit as we're... How many people feel okay with what we talked about so far? Asymptote. What you have to do is a sign analysis test. Here's what you do with a sign analysis test. You put the numbers that will make the numerator and the denominator equal to 0. Put that on a number line. What numbers am I talking about here? Put that on numbers that will make the numerator and the denominator equal to 0. Put that on a number line. What numbers am I talking about here? 5, definitely. 5, because we want to find out what's happened at 5, and that was our problem area. So 5 is going to have to go over here somewhere. So far, side of our limits and using those things.
поколений мужчин, выращенных женщинами? Поможет ли другая женщина в решении наших проблем?
when I give you a problem very much like, oh, all right, good. Woo. Yeah, kind of obvious. Change basically, then a one-sided limit will certainly exist. Agreed? So a limit existing is stronger than a one-sided limit existing. Does that make sense to you? Well, here's the cool part about that then. And this, a lot of you were asking me, how do I find one-sided limits? Check it out. If you know for sure that a limit exists, then the one-sided limit will exist. Plug in 3. Ignore the from the left. Plug in 3. What do you get? What I do is take an arbitrary angle. I can't be specific because, of course, you want this to work all the time. "30 seconds. If you do plug in this one, okay, I can say, well, was that apparent? Times this. Continuity. Here's the layman's term definition of continuity. A function is continuous if it has no holes, breaks, or asymptotes. That's pretty much it. If you can graph it by not picking your pencil off the paper, you would say it's continuous. So that's what we're talking about. So continuity says the curve's continuous. If it doesn't have any holes or breaks or asymptotes. Now, would you like me to give you a more precise definition than that? Holes, breaks, and asymptotes? Yeah. That's understandable, right, though? Hopefully. It doesn't have any holes in it, it doesn't have a gap, and it doesn't have any asymptotes in it. That if you don't have those things, then it's continuous everywhere. If you do have those things, it'd be continuous most places, just not at those specific points. Here's what continuity is mathematically, though. So more specifically, a function is continuous if three things happen. First, oh, sorry, you know what, and let me say at a point. I need to add that on there, otherwise it's not going to really make a lot of sense. So continuous at a point C if, so continuous at point C if, firstly, I hope this makes sense to you. Firstly, if the function is defined at that point, this has to exist. How can you have continuity if the point doesn't exist? Does that make sense to you? So we'd say it's continuous at some point C if you can plug in C and you get out a point. That's what that says in English. So if f of C is defined. You plug in C, you get out a point. That's what that means. Number two. Number two. The limit has to exist at that point. So that means that the function is from both sides around point C. Remember, point C is like your input, right? Around point C, the function is going, no matter what, to the same spot. Does that make sense? It can't go like this. That wouldn't be continuous because you have that jump. You with me? So the limit has to exist and around that point C. So not only does C have to be defined, the limit of f of x as x approaches C must exist. And thirdly, this thing has to equal this thing. So f, a function f is continuous at point A or point C if three things happen. Firstly, the point exists. What this means, again, last time, is if you plug in C, you get something out. Secondly, the limit exists. That means the function is going to the same place from left to right as you approach C. Thirdly, where you approach is this point. That's what that says. Where you approach is that point. So it means the function's going to a point, the point exists, and it's right between where the function's going. Okay, that's what that says. If that happens, what that means is you're going along your function, you get to a point, you fill in the point, you keep on going. Make sense? So there's no hole there. There's no asymptote. And that also works for asymptotes, right? Even the limit existed in infinity, there's no point at infinity saying you would have a break. You can't make that little jump. Let me give you some pictorial examples on what this looks like. You ready for it? So. Let's try to apply this, the question I asked you to this over here, what I told you about continuity. So number one, does the point exist at x equals c? Is there a point there? No. So already we fail number one. That right there says you're not going to be continuous because you fail number one. Is number two satisfied though? Does the limit exist? Yeah. Yes, it's going to the same value from left to right. So limit's there. But when you ask this question, is the limit equal to the function value? No, because there's a hole. It's not even there. So there is no point. Number one fails, and therefore number three fails. This is not continuous. So we'd say it's not continuous, wait, all over the place? Is it not continuous all over the place?
Not continuous
at C. Is it continuous here?
Yes.
Absolutely. Actually, most of this function is continuous. It's just that little point that's not continuous. What this is called, when you have a hole, remember talking about holes? It's called a removable discontinuity. So this is not continuous at C. And we call it a removable discontinuity. What that basically says is you have a hole. A removable discontinuity is a discontinuity that you could fill in with a single point. Let's try another one. Let's check our three necessities for our limit to for our function to be continuous at a point C. Firstly, is number 1 satisfied? Do we have a point at C?
Yes.
Yes, we do. Is number 2 satisfied? Does a limit exist?
No.
Limit exists says we're going to the same spot. It means it has to look like this to get it. Does it look like that? It looks like this, right? That's a problem. So does this side meet up with this side? If it doesn't, then the limit doesn't exist. So is number 2 satisfied? No. If number 2 is not satisfied, number 3 can't possibly be satisfied because this is non-existent. So this fails continuity. So we'd say, yeah, this is not continuous at C, for sure, it's not continuous. But is it a removable discontinuity or not? No, even if I put another point up there, it's not going to make a difference, right? I'm not going to be able to continue my function with one single point. This one I could. Just put it right there, you're good to go. It's like filling in the hole. But here you can't do that. This is not removable. This is like a jump continuity. You're jumping from point to point, or from one part of the function to another.
Jump continuity or discontinuity?
I don't know if they call it a jump continuity in your book. It might, but that's what you're doing is you're jumping. So we'll say that's a jump discontinuity. This one's removable discontinuity. How about this one? Let's check our 3 statements. Number 1, is the function defined at point C? Is the function defined at point C? Really? Defined? You can plug in C and get a point?
No.
No. What if I did this? I said, okay, there. Is the function defined at point C? Yes, it is now. There is a point. You plug in C, you get that specific point. You with me? Does the limit exist? So number 1 is satisfied. Is number 2 satisfied? Does the limit exist? Are you going to the same spot from left to right? Going to infinity? Yes, limit exists. So number 1 is satisfied, and number 2 is satisfied. Would you agree with that?
Yeah.
This is why we need number 3. Is number 3 satisfied? Does the limit equal the value of the function? The limit equals infinity. The value of the function equals this right here. Are those the same thing? So number 3 fails. So we've had a case where number 1 fails, where number 2 fails, and now where number 3 fails. So you see those examples, yes? This is called an infinite discontinuity. So we'll say this is at infinity, or infinite. Hey, what about this one? What if I put a point, if I put a point up here, but it didn't close in the circle, would that be continuous at that point? No, it would still jump. That's still a removable discontinuity, though, if I redefine the point. So if I say, okay, you know what, I'm just going to move this point from here to here, redefine it, then we'd say that's still a removable discontinuity. How many people understand the different terms that we have here? So basically we have 3 different kinds of discontinuities. Those that have asymptotes, those that are jumps, and those that are holes. We mostly deal with these 2. This one would be like a piecewise function. We are mostly over here when we're dealing with rational functions. That's usually what we have. Stuff we can cross out. Well, actually we have that. Stuff we can cross where we get rid of the problem in our limit, and stuff that we can't cross out where we do a sign analysis test. I've showed you both of those things before. Do you remember them? All right. Shall we check? Let's check some functions to see if we can tell whether they're continuous or not. Are there any questions about our necessities for continuity here or these graphs over here? Okay. Yes?
When you said that, when you had the point on the first one,
Sure.
below the hole,
Yeah.
and you said you could move it up to the hole, but it did.
We have to, well, not move it up to the whole, we're redefining. We're saying this would be a piecewise function right now, or some very special function. We redefine this in some way so that this is no longer here, but it fits in that hole. That's called the removal discontinuity. We've removed this point and placed it in the hole, basically. We've redefined it somehow. But keep in mind, you are redefining your function just a little bit. Okay, so we're going to ask, are these following functions continuous at x equals 2? Let's see. So first one, how about f of x? Is that continuous at x equals 2? Basically, is it defined at x equals 2 is what you would check first. Is it defined at x equals 2? Can you plug in 2 and get something out? So that would fail. This is not continuous. In fact, if you remember, I think we've had this problem in one very, very similar to it. What this is, by the way, can you determine whether that's a hole or an asymptote? Could you figure that out? Why is it a hole?
Because it's
It does, yeah. This is x plus 2, x minus 2. So your function is really x plus 2. Do you see where the x plus 2 is coming from? Use your difference of squares, cross out your x minus 2s, you're going to get x plus 2. That's really what this function is. Well, at least that's what it looks like, is x plus 2 only when I plug in 2, so if I cross those out, I'd say, well, yes, f of x equals x plus 2. But I hope you remember what I told you about domain. Domain has to be from the original function, not your brand new function. Remember when we talked about that? So x can't be defined at 2. We tried that up here, it didn't work. What this says is, if I were able to plug in 2, that's what I get out of it. 4. Now, am I able to plug in 2? So what that says is, if I were able to plug in 2 and I got out 4, I have a hole at 2 comma 4. Can you make that jump? You okay with that idea? That says, all right, normally I would be this function, but I know I can't plug in 2. That means I can't get out the number 4. I can't get out that value. Just to reinforce a concept, would this be continuous at x equals 1? How about x equals 5?
Yeah.
How about any other point besides 2? Absolutely. We're just talking about 2 right now. Now let's move on to the next function. These look confusing, but here's all this says. This says, for everywhere except 2, you're now this thing. We have that here. But now at 2, I have a point 3. So let's check the continuity now. Is number 1 satisfied? Is the function defined at my point x equals 2?
Yes.
Absolutely. It's right here. That's the definition. Does a limit exist? Does the limit exist? Yes, the limit exists. The limit exists. But now this point is 3. So when I go over 2, it says I'm at 3. That's what this one is right now. So it says, is the function defined at the point? Absolutely. Does the limit exist for my function around that point? Yes, it does. Is the limit equal to the function value? So is this one continuous?
No.
No. No. Everywhere else, yes, but not here. So no.
Now, what kind of,
No.
would that be a jump or
This would be a removable discontinuity. I'm going to show you why right now. Okay. So firstly, we tried a point, right? We have this function and we have this hole in it. So if I cover that up, this is my original f of x. True? I tried to plug in a point. Did I make it fit right? No, it doesn't fit right. Let's try the next one. h of x says, okay, now, it looks almost identical to g of x, except instead of having x equals 2 defined at 3, we have x equals 2 defined at 4. Tell me, does the 4 fill in the hole?
Yes.
So by making a piecewise function and defining just one single point, we go, oh, well, how about this? Is the function defined at that point? Yes, it is. Does the limit exist at that point? Yes, it does. Is the function equal to the limit?
Yes.
That meets all 3 qualifications for having continuity of that point. Therefore, we say yes. That's a removable discontinuity. It means you identify one point that fills in the hole. Bless you. Okay, if a function is continuous at each point between a certain interval, like a, b, we can say it is continuous on the interval a, b. So let's say if f is continuous at every point between a and b, then f is continuous on AB, the open interval. If f's continuous at every point, that means like over here between this range of numbers, It's continuous at every single point, right? There's no jumps, there's no holes, there's no asymptotes. It is continuous. We'd say it's continuous on the open interval. The question I have is, what about the endpoints? And we're going to look at that right now. So what would happen, because right now this is open, right? It's not including the A and the B. How can we determine whether or not to include those endpoints with brackets or whether we can't? And we'll look at that just briefly. So F's continuous at every point, okay? We have F is continuous on the interval A, B. But what about the endpoints? And let's say this is our function path. Hey, would you say this function is continuous between A and B without including the endpoints? For sure, at every single point. There's nothing wrong with it. Now, would you say it's continuous at the point B? Yeah, the point's there, right? The point's there. Now, we don't have, here's the weird thing. We don't have a full-on limit because we don't even have one side. However, the one-sided limit from the left goes to the same value that the point B is defined at. Does that make sense to you? So it's going to the point and the point exists. You with me? How about the left-hand side? Does the limit, is it continuous at the point A? At the point A. The limit exists from the right, sure. The point exists, but is the limit equal to the point? No, this would be kind of like a jump, right? If I had this going this way, that would be like a jump continuity. You have that point that's not there. Now, it doesn't have that other side. So we'd say this is continuous on, well, how would we write that? If it's continuous from A to B, but it includes B and not A, how do I write that? One bracket, one parenthesis, sure. So this is continuous on, I know it goes from A to B. Again, does it include the B? The B.
Yeah.
The B, yes, because the point's there, the limit's there, it equals the same thing. How do I show that? Is that the bracket or the parentheses? That's the bracket. That says I include the point B. Now it can't include the point A because the limit exists from one side. The point is there, sure, but it's not the same. In general, here's what you have. I'll give you a more mathematical definition of this. In general, here's what has to happen. If it has to be continuous from the left at point C or continuous from the right at point C. So for continuity from the left, you'd have the limit as x approaches C from the left of f of x has to equal f of C. That's very, very similar to the third qualification for continuity that we just had, only this time it's a one-sided limit. So basically we're just checking one-sided limits and making sure they go to the point that is defined and that the point is actually defined. This is like the situation we have at point B, okay? The limit from the left exists. The function at C, well, in this case that's B, okay? The limit at the function at the point exists and they are equal. This is like the situation for point B. Like point B. For being continuous to the other endpoint from the right, at point C, well, it's just the opposite limit. You have to have the limit from the right-hand side. The function has to be defined at that point, and it's got to be the same. This is like f of a. The limit has to exist. It does. The point has to be defined. It is, but they would have to be identical. So this is like the point A situation. In our case, it's not continuous at the point A. Would you like to see an example on how to prove this with a closed interval? Okay, I'll show you how to do this. It's a three-part. It's not hard. Okay, it's just a three-part proof. What we're going to do is we're going to prove continuity for an open interval, which is relatively easy. We're going to prove continuity for the left and the right intervals, which are both relatively easy. So we have basically three limits to do. We've got to prove continuity in the middle, then prove continuity at the endpoints. So I'll write the question on the board, and then we'll go for that. So I want to prove that this function is continuous on -4 to 4. Inclusive, closed interval. This again involves three parts. The first step, we've got to check the open interval. Got to check the open interval. The next step is going to be check the right endpoint. The next step is going to be check the left endpoint. So I'll write these out and we'll start here next time. So the right endpoint would be +4 from the left. The left endpoint would be -4 from the right, because you're going from the right on that. We'll figure out how to do this next time. I'll show you each little piece of this, and we'll determine that it is, in fact, continuous from -4 to 4 inclusively. All right, so hopefully you remember from last time we were working on this problem. We want to prove that that particular function is continuous on a closed interval. Now, in order to figure out if a function is continuous on a closed interval, we have to basically check three things. We've got to check first the open interval to see if there's any holes or asymptotes on that open interval. The endpoint's a little different though, because when we check continuity, we're really checking limits, right? Right? Yeah. So we're checking limits. And at an endpoint, a full-on limit does not exist because there is no function coming from the left or maybe the right-hand side at a certain case. So what we do at our endpoints is we check a one-sided limit. So what that means is that, sure, we can check the limit on an open interval just fine, because there's always a point to the right. That means that we can always find the limit of that. However, when we talk about endpoints, we've got to check one-sided limits and just see if they match up. Now, it's not a hard thing, so don't think it's going to be super, super hard. It's just you have to do it 3 points to actually prove it right. You with me on that? I'll show you how to do it. You'll see it's not really a hard thing to do. First thing we're going to do is check the open interval -4, 4. So we're going to check this thing to say that, okay, at least we know we're continuous from this point to this point, but not inclusively. Then we'll have to check the endpoint, -4, and we'll check the endpoint, +4. If we're going to check, I want you to understand the notation here. If we're going to check -4, understand that -4, we're going to have to be coming from the right to check that. Do you understand that? Because from the left, nothing exists over here. So we have to be coming from the right. Does that make sense? For +4, that's over here. We're going to have to be coming from the left. That's where this from the left and from the right are coming from. There is nothing to check over here. It's from the left-hand side. We're saying the function we care about the other side of that. Do you understand the notation for our limits? All right, so let's do the open interval. I'll show you how to do this. It's really just a very, very basic point, proof. Here's how you start out. What we want to prove is that the limit of f of x equals f of c as x approaches c. That's what we want. If we can show that, then we've proved that the limit exists, the function exists and they equal each other. That will prove the whole thing. That will be the 3 cases for continuity, or the 3 points for continuity. The limit exists, the function exists, and they equal each other. You with me on that? So let's do that. What we're going to do is start here and try to work our way to there. So the limit as x approaches c of f of x is really the same thing as the limit as x approaches c of the square root of 16 minus x squared. Are you okay with that so far? Now, given that c is some point between -4 and 4, given that c is some point between -4 and 4, can we plug in c and be okay? What do you think? Let's say c was 5. Would that be okay? You'd have a negative inside your square root, right? That would be a problem. But because c is between -4 and 4, are we going to have a negative inside of our square root? Okay, so what we can say is that if c is between -4 and 4 for any c, then this is possible. Here's where you make the jump. If there's not going to be any issues in your specified open interval, open domain, then you can make the jump and say, okay, we can actually evaluate that limit at any point c. Do you believe me? If I gave you any point between -4 and 4, could you plug it in and be okay? Absolutely. Here's what that says. It says, if Mr. Leonard gives me any point, I can plug it in and be okay. Where did the c come from? It's not a trick question. Where did the c come from? Yeah. Where's x approaching? And you know for a fact that c is between these numbers, right? That's what I'm telling you here. And you just told me that no matter what I gave you between there, i.e. c, no matter what I gave you, you could plug it in, right? That's what you're saying here. You're saying the limit is okay to evaluate because this is between those numbers. I have no problems. Now check this out. Is this not f of c? Isn't that just f evaluated at c? You've just proved it. We've just proved that the limit of f of x as x approaches c equals f of c. We've proved that. That's checked for that. That's all you gotta do. Just make sure you take that, plug in the c, and see that it's exactly the same. You okay with that one so far? Hope so. It's not. You might think, well, that's kind of trivial. It's really not trivial. I mean, we're actually thinking whether this point's in there. Sure. We're thinking whether it's going to have any problems. It doesn't. Therefore, we can take any c, plug it in, and that is f of c. That's what we're trying to prove. We're trying to get to this point. So that does it for us. Now, as far as the one-side limits go, as far as that goes, if we're going to the right, from the right to -4, we're getting really, really, really close to -4. Would it be okay if I just plugged in -4? What's 16 minus -4 squared? Is that okay? Can you get a 0 inside of a square root? Is that acceptable?
Yeah.
Then yeah, that's a one-side limit. That's going to exist as well. So this is going to equal 0. That's equal 0. You're going to plug, well, I can show you the extra step if you want. You said it's okay to even evaluate that at 4. It exists. The limit's going to exist one-sidedly from the right. That's the same thing as saying, oh, well, that's 16 of minus -4 squared. That equals 0, which equals f of -4. Because you're just plugging it in. That's also saying the limit as x approaches a certain number, in this case an endpoint, is equal to the function's value at that point. That's another check. We can do exactly the same thing for 4 to the right. If you plug in +4, is that going to have an issue over here? No, that means that as we get closer and closer to +4, this function's getting closer and closer to 0, true? So we can plug that if the one-side limit's going to exist. It says it's going to that value. So this would be, well, square root of 16 minus 4 squared, which is 0, which is exactly f of 4. That's what you're trying to prove. You're trying to prove that I can plug in any number, that's what that says, and it equals the function at that value. So I can plug in the endpoint, but that is true. Getting closer to positive 4, this function's getting closer and closer to 0. If you plug in positive 4, is that going to have an issue over here? No, that means that as we get closer and closer to positive 4, this function's getting closer and closer to 0, true? So we can plug that, that the one-side limit's going to exist. It says it's going to that value. So this would be, well, square root of 16 minus 4 squared, which is 0, which is exactly f of 4. That's what you're trying to prove. You're trying to prove that I can plug in any number, that's what that says, and it equals the function at that value. So I can plug in the endpoint. Look at this is what this says. I can plug in the endpoint, and it gives me f of when I plug in the endpoint. That's all I'm saying. I can plug in the endpoint, and it gives me f of when I can plug in the endpoint. What this says in general is, okay, the limits exist in all cases, one-sidedly and in general, and the limits equal the functions at every single value. If that happens, you're continuous the whole way through, not just on the open interval, but now on the closed interval because you included endpoints, and that's how you check it. Did that make sense to you? Were you able to follow that? It might seem a little confusing. Why do we do this? Well, you kind of have to do it that way. You have to check a one-sided limit because you can't technically do this for the whole thing because you don't have a limit at every single point, full-on limit from both sides at every point. You have it here, but you don't have it here. That's the difference. That's why you have to check the endpoints. Now, a couple properties about limits that we're going to discuss. Were there any questions on that, by the way? As my back is turned to you so I can't see you raise your hand. Any questions? Seriously. All right then. A couple properties. Let's say that we got two functions, f and g.